Good afternoon, everybody. I hope you're having a great day so far. Today we're looking at lesson 31.06, which is graphing functions. And this lesson can be found on page 4 of your current lesson handout. If we take a look at our task today, we have one function that we would like to graph without using a graphing calculator. Just make a note, though, that I was still editing this document as late as Monday morning. So if you had already downloaded the document before I finished editing it, there might be some changes. And one of the changes is going to be that the function should be f of x equals x to the third multiplied by x squared minus 7. And as late as Sunday night, it was a different function, and then I looked at it Monday morning and decided I wanted to change it. So that's the function we're doing. Now, everything that you were doing Monday, and I'm going to list them off right now. What we were doing Monday is finding x and y intercepts, finding equations of all asymptotes. We were determining if a function had symmetry or not. We were also using the first derivative to complete a first derivative chart so that we could determine any max-min locations. And we were also using the second derivative to determine a second derivative chart so that we could determine any inflection point locations. Two things we were not doing on Monday. One was we were not too concerned about finding y coordinates. Well, since we are asked in this lesson to sketch the function, we are going to need to know the y coordinates of these important points, of the points that are max points or min points, or of the points that are inflection points. And the other thing was, at the end of the examples that we did on Monday, I just showed you what the graph looked like to, I guess, show you that everything we've learned in the exercise of doing all these little things, everything we did matched up with the graph of the function. This time, we have to come up with what the graph of the function looks like without peeking at a graphing calculator. We have to look at all of our work and try to put all of the pieces together. Now, in your classroom folder, the one that's shared, there is a file I put in there. It's a 2-page PDF file called Graph Summary. And it's a useful thing to refer to when you're doing these graphing problems in this section. It might not be a bad idea for you to print this out and do your work right on it, but you certainly don't have to. This is just meant to help keep you organized. On one page, I have all of the information where you're going to summarize it, and then on the bottom of that first page, there's lots of room for work. And when you take a look at the next page, at the top of the next page, there is also lots of room for work. Then at the bottom of the second page is where you can do your sketch. There's a horizontal line there, and I will get to what that's used for in a little bit. All right, so let's take a look at the function in terms of all of these pieces of information. Now, I have, again, taken the liberty of finding the first and the second derivatives and put them in my summary chart here, because I don't want to spend valuable time differentiating this function. You know how to differentiate. If you want, you can differentiate it on your own to make sure that you get the derivative, and then differentiate that to make sure that you get the second derivative. But you'll have to trust me that those derivatives are right. So let's start filling in the information. What do we know about the domain? Well, when I look at this function, it contains a cube root. X to the 1/3 is a cube root. And I'm allowed to cube root positive numbers, negative numbers, and 0. And then in the brackets, I also have x squared minus 7. Well, what that's telling me is I can use any real number for x. There are no restrictions. There are no non-permissible values. What about the y-intercept? Well, the y-intercept is found by replacing 0 with x in the function. We have y equals x to the third multiplied by x squared minus 7. So to find a y-intercept, we let x equal 0, and we'll get the y-intercept equals 0 to the third multiplied by 0 squared minus 7. You're going to get a y-intercept of 0. While I'm talking about intercepts, we can refer now to the x-intercepts X-intercepts are found by letting y equal 0. So if I take that function and I change it to 0 instead of y equals x to the third multiplied by x squared minus 7, I have two factors. The only way that the product of the factors could be 0 is if the first factor equals 0 or if the second factor equals 0. You can see then that we have a number of x-intercepts. The x-intercepts will be 0 and plus or minus root 7. So we can add that information to our list. It's going to be useful information in terms of graphing the function. A y-intercept is 0, and we have numerous x-intercepts. We have 0, positive root 7, and negative root 7. I notice as I look at this that I have the range up here in the summary, but the range is not given on your handout. The reason why the range shouldn't be there is it's something that you can't really find without actually completing the graph of the function. That's the only way you're going to find the range. So if we look at the asymptotes, there aren't any asymptotes because this is not a rational function. In other words, there's no denominator in this function, which means you cannot have any type of asymptotes. So there are no asymptotes. The only other thing we have to do here before we get to the derivative charts is to talk about the symmetry. Well, if we have y equals x raised to the third multiplied by x squared minus 7, that's the original function. This is f of x. What we want to do is find f of negative x and compare the result to what the original function is. F of negative x means we're going to take negative x and place it everywhere in the original function where there was an x. A cube root of a negative number is still a negative number, so the cube root of negative x will be negative of the cube root of x. What this means is negative 1 multiplied by the cube root of x. And then in the brackets, when you square negative x, you get positive x squared. And if we compare this to the original function, we can see that this is the original function. And that means that f of negative x is equal to negative 1 multiplied by the original function, and that means that the symmetry is odd. We can add that to our list. We have an odd symmetry. And now what we need to do is do our first and our second derivative charts. Our first derivative is given in the top right corner of your view right now. We can make a note that there are three critical values for this derivative: plus and minus 1 and 0. We have a critical value of negative 1, we have a critical value of 0, and we have a critical value of positive 1. That means that since the domain is any real number, we're going to start at negative infinity and move all the way to positive infinity, making a cut or a slice every time we hit a critical number. So the first critical number is negative 1. We'll go from negative infinity to negative 1, then from negative 1 to 0, then from 0 to positive 1, then from positive 1 to positive infinity. And across the top, we can put all of the factors of the derivative. 7 is a factor, x plus 1 is a factor, x minus 1 is a factor, and 3, x raised to the 2/3 is a factor. We're doing this, of course, so we can determine whether the derivative is positive or negative, and that leads to information about whether the function is increasing or decreasing, which in turn leads to coordinates of any maxima or minima. I'm going to group the 7 and the x plus 1 together here. So it's negative, then positive, then positive, then positive. The x minus 1 is negative, then negative, then negative, then positive. 3x to the 2/3 is going to be positive everywhere because we are raising x to 2 over 3, which means we're going to square the x at some point. We're also going to take the cube root, but the squaring will eliminate any negatives. That tells us if we multiply from negative infinity to negative 1, if we multiply negative times positive, we get a positive first derivative. Then the derivative is negative. Then the derivative is continuing to be negative. And afterwards, the derivative is positive. What that tells us about the function is increasing, then it is decreasing, it continues to decrease, and then it increases. What this means is that you have a maximum occurring at -1, and you have a minimum occurring at +1. Well, I'm going to go back to my summary now. We have a maximum at -1, and we have a minimum at +1. Well, now what I'm going to do is find the y-coordinate. So I'm going to deal with putting -1 in for x in the function. The function is f of x equals x to the 1/3 times x squared minus 7. So I'm finding out what the y-coordinate is at that maximum location, which is where x is -1. I'm going to get -1, the cube root of -1 is -1, and then multiplied by -1 quantity squared is 1, minus 7 is -6. When I multiply those two together, I get +6 for a y-coordinate. Put a 6 here. Now, I don't need to repeat that process to determine the y-coordinate of the minimum. And the reason I don't need to do that is I've already established that the function is odd. By finding the symmetry, it allows us to save some time with some of our work. An odd function means that if you go from an x-coordinate to the negative of the x-coordinate, the y-coordinate will become the negative of the y-coordinate. So if we go from x equals -1 to +1, that means y must go from +6 to -6. So now we know the coordinates of the two extreme values. We did have another critical point for the first derivative, which was x equals 0, but it didn't lead anywhere. Now we have to look at determining inflection points and concavity, which means we're going to look at the second derivative. Now, when you look at the second derivative, there's only one critical point. The critical point for the second derivative is 0. There's no value of x that makes the numerator 0, and the only value of x that makes the denominator 0 is 0. And that means our second derivative chart here, everybody, will be fairly simple. It's only going to contain two intervals. We have to go from -infinity to 0, and from 0 to +infinity. We can put all of the factors of our second derivative across the top of our chart. We have 14 multiplied by 2x squared plus 1, and we also have 9x to the 5/3. I'm going to choose to group the 14 and the 2x squared plus 1 together. This quantity will be positive everywhere simply because when you square x, you're going to get a positive. And if you multiply that positive by 2, it's still positive. And when you add 1, it's still positive. And when you multiply by 14, it's still positive. Now, the monomial factor of 9x to the 5/3 has an odd exponent, which means if the base x is negative, when you raise the negative to a power of 5 at some stage, and then take the cube root, you're going to be left with a negative. However, if x is positive, then you're going to be left with a positive. This is telling us something about the second derivative. When we multiply these two factors, positive times negative is negative, positive times positive is positive. That tells us that the function is concave down everywhere from negative infinity to 0, and it's concave up everywhere from 0 to infinity, and that must mean that there's an inflection point at 0. And now I can go put that information in my table. The inflection point, there's only one of them, is at 0 comma something. Well, if I go ahead and find f of 0, f of x is x to the third multiplied by x squared minus 7. So f of 0, which is going to be the y coordinate of the inflection point, f of 0 is going to be 0. And I mean, we kind of knew that because the x-intercept is 0, and an x-intercept of 0 is the origin, which is at 0 comma 0. So now what we want to do is we want to use all of this information to come up with a picture of the graph. And the first time you do this, it's kind of hard to believe that we're going to be able to tell what the graph looks like by just looking at this information. We're not going to make a table of values here. We're simply going to use the information that we're looking at along with our first and second derivative charts. The first thing we want to do is look at all of the x values of the important points. I mean, the maxima and minima occur at x equals -1 and +1, and there's an inflection point at 0, but the x-intercepts are at +√7 and -√7. So when we scale our axis on paper horizontally, we have to make sure that we're going to include the square root of 7 and the negative of the square root of 7. So we should probably evaluate the square root of 7 on our calculator to find out approximately what it's equal to. The square root of 7 is approximately 2.6, so it's between 2 and 3. And that means when we scale our grid here, I have to go to at least that far on the right and the same distance on the other side. So now we have to set up a scale on the x-axis to include all of those points. The square root of 7 is approximately 2.6, so when we set up the numbers on the horizontal axis, we've got to go up to at least that far. And given that that's just an x-intercept and something might happen after that, I would recommend going up to 4, maybe even 5. Now, when you put the numbers on the x-axis, you don't want to do so just freehand. You want to probably take a ruler or some other measurement that ensures that you're taking the same distance as being 1 everywhere. So I guess if I choose 2.5 centimeters being 1, this would be 1, this would be 2, this would be 3, this would be 4. It doesn't have to be exact, but you want it pretty close because you want your graph to look okay. 1, 2, 3, and 4. And now what we're going to do is start plotting some points. We know, for example, that the graph goes through the origin. We also know that the origin is an inflection point, but we'll just keep that in the back of our head. We know that there's an x-intercept at √7 and an x-intercept at -√7. Don't forget, √7 was approximately 2.6, which means it's approximately here. I don't care if you put it exactly where it should be, but just make sure that when you graph it on the other side, you're putting it in a symmetrical fashion. So those are our intercepts. What else do we know? Well, we know that there was a maximum at -1, 6. So when I go over here to -1, there's a point up here that is a maximum point. And that happens to be at y equals 6. This is why I said a little bit earlier, I believe, you don't need to worry about scaling your y-axis. It's going to take care of itself. Now we also have at +1 a minimum at -6. So you want to make sure that you scale your vertical axis the same way up as you do down. I'm going to just cheat a little bit here because I can erase things. So you want to make sure that this distance is the same above and below the x-axis. just to ensure that your graph ends up looking symmetrical. So we had a minimum at 1, -6. I can put that point down now. Now, what is the line that's horizontal at the top for? If you were to take a look at your first derivative had a critical point at -1. It had a critical point at 0. And it had a critical point at +1. And if you go back to your first derivative chart, what you will discover is that in the interval from -infinity to -1, the first derivative was positive. And if the first derivative is positive in this interval, that means the graph of the function, when we sketch it, must always be going up to that point. We discovered that in between -1 and 0, the first derivative was negative, which means that the function in this interval is going down. Then we discovered that even though 0 was critical for the first derivative, nothing changed. The function continued to decrease because the derivative was still negative. And then we discovered that from 1 to infinity, the first derivative was back to being positive, which means that the shape of the graph has to be increasing. Now, if we take a look at the critical points for the second derivative, there was only one critical point for the second derivative. And the critical point for the second derivative was also the same as the critical point for the first derivative, 0. What we discovered is that the second derivative was negative everywhere from -infinity to 0, which means that the shape of the graph from -infinity to 0 is concave down. We discovered then that from 0 to infinity, the shape of the graph was concave up. These things that I've drawn at the top are an aid to help you sketch the function. And they're also nice to have because once you do sketch the function, you can compare your graph to those shapes. So take a minute here and ask yourself how you would sketch this function so that it would be increasing all the way to -1, decreasing all the way to +1, then increasing all the way to infinity, but still have those concavities that are indicated in blue. And the answer is that the graph will have to look something like this. And that's essentially what the graph looks like. All right, so on page 240, there are 12 different functions. On page 245, in question 5, I believe there are 6 different functions. And each of these questions ask you to do the following. It says something like, under the headings A through H, sketch the functions. Well, I didn't break it down by letter, but what it's asking you to do is to determine everything about the function and come up with a sketch of the function. So what I'm saying that you should do between now and Friday, when we do one more that will be more complicated, is pick a function, or 2, but pick a function and see if you can come up with a sketch of the graph by determining everything that we did in this example today. Now, if you find that you followed today's work quite easily, you might want to pick a function that looks a little more challenging. If you're struggling with this, pick a function that seems easier. Numbers 1, 2, 9, 10, 11, 12 are very interesting functions. And on page 245, 5F looks like it's interesting as well. By interesting, I guess I mean challenging. So pick one of those for sure. Get some practice doing this You can certainly do 2, and you can do more than 2 if you like, but do 1 for sure. And then on Friday, we will do one that is a little more interesting. So I hope you're able to follow all of that, and I hope you have a fantastic rest of the day. We'll talk to you later.